Hello everyone, thank you for watching this video. My name is Sebastián Montoya. I'm a graduate student at the Civil and Environmental Engineering Department at the University of Maine, working with the professors Aaron Gallant and Bill Davids. Today I'm going to talk about some of the results that I got during my PhD, whose main focus is on flexural strength of micropile thread connections. So to start with, uh, we are going to focus on one particular kind of micropiles that have permanent steel casings. So uh, this kind of micropiles can develop high geotechnical capacities, tension and compression that are suitable for challenges of surface conditions at site with limited access and at situations with low head clearance. The way that micropiles are installed is by taking segmental pieces of the steel casing, typically 5 foot long, drilling them into the soil and connected one piece with the next to achieve the desired depths. The way the connection is made is by means of a thread connection. So a thread detail is machined into the end of the casing, being one end a pin or a male end, and the other side a bolt or a female end. Typically, those micropiles are filled with grout, and in most cases, they incorporate a center rebar. The picture on the top right is provided by Keller North America and showing the installation of this kind of micropiles at the basement of the building so that you can have an idea of the small they are and the size of the equipment that they need. What makes them so great is the capacity to connect different small pieces. That's the thread connection, but that also happens to be its weakest part, as when they are subjected to lateral or bending loads, it's likely that failure takes place on the joint. So at the current state of the art, there's no generally accepted method to estimate the bending capacity of a thread joint, and that's what we are trying to address at the University of Maine by means of a full-scale testing. So the picture in the left is showing an actual test setup. The cartoon on the bottom right is depicting it in more detail. So what we do is that we take one of these micropiles, which is composed of 2 segments, one with a box end and the other with a pin end, thread together by a thread joint in the middle, and then we subject them to bending, increasing the load until failure of the joint takes place. Measurements that we do where this happens is displacements at 5 different points, as they are the supports, the loading points, and the midspan, measurements done with string potentiometers, rotations at the end of the micropile by means of inclinometers, measurement of the load by means of a load cell, and detailed strain fields in the neighborhood of the thread joint using digital image correlation. Before we can go into the test, we have to assemble these micropiles elements. And to do that, we try to mimic the installation conditions and field. So we receive the steel casings of our facilities in the Advanced Structure and Composite Center. Again, these are composed of 2 pieces that thread together. So they came hand tied from the production plant. And at the university, we use an hydraulic wrench to apply an extra torque and make sure this connection is really tight. And at the same time, trying to represent the torques that they are subjected when they are being drilled into the soil. Then we stand up all the micropiles up vertically, stacked vertically, so that we can provide gravity grouting, similar at how they are filled with grout in the field when they're installed into the ground. And for some of those micropiles, we introduce a center rebar. This is a video of the actual test. So it's showing us the load progress. We cannot see effectively what the deformations are, but we can see very soon how failure takes place right at the joint. So the focus of this study is to understand how different thread details impact on the overall connection strength and the kind of failures that we are attaining. So for that, we had played with different parameters as they are the casing diameter, the wall thickness, different thread lengths, uh, wall thickness at the pin, thread heights, and thread shapes as given by their thread flange angle. That allow us to cluster our different micropiles into three different kind of connections. A connection type A, where we have a straight wall and a B-like or a trapezoidal shaped thread as shown on the right. Then we can do type B, which is the same kind of thread, but now we introduce a taper wall that as we do thicker towards the beginning of the connection and thinner at the end. Or type C, where we have again a straight wall, but in this case we use square threads. Because of time limitations, we are going to discuss today results on threads type B that have 7 5/8 inch in outer diameter, and we are going to work with two different thread lengths, short threads of 2 inches, nominal thread connection, that's the distance from shoulder to shoulder of the connection, and 3 inches, that will be your long threads. So for the short threads, the most insightful measurements come from the VIC strength field. From the strength field, we are able to derive the bond misses strength, which is a measure of how much yield has stand into the connection, as this is shown on the picture of the upper left. Vertical is for depth position, so we are having a front view of the connection. Lateral axis or horizontal axis is for our longitudinal position through the micropile. Blue means low strains, while yellows go to large strains. And along with the strain measurement, I have a sketch of the thread details so that we know where the connection are relocated. On the right side, I have same kind of graphic, just showing for the hoop strain. As I'm going to discuss later, the amount of yield that is developed on the connection is related to the amount of hoop strain that we are developing. At the bottom, I have different cross sections of the bond misses strain that is being developed, and this cross section correspond with different thread positions through the connection, going from the first thread to the second, and so on and so on. So for the short threads, what we observe is an early development of high strains towards the end of the connection. This scenario, it's congruent with the development of hoop strains. What's happening is that at failure, our connection is still connected, still together, but is not able to transfer more load. The threads had a slip one over the other, and a gap is created at the shoulder of the connection, and it's shown by the sketch at the bottom right. The consequence of this thread slip is that large hoop strain, large dilation of the box has to take place, and that introduces a lot of yield. Consequently, the box plastify and is not able to take more load. When we increase the thread length, we observe a different pattern arises. So in this case, we develop less hoop strain, that means less dilation. And in this case, the yield is concentrated towards the beginning of the connection where the actual strains govern. Finally, the failure that we observe is rupture. As the dilation is limited, the threads are still in contact, but we reach the full capacity of the pin, developing a crack and eventually disrupting the connection. This depicts essentially two big differences, just introduced by changing the thread length. As if we pay attention to the failure load on the first and the short threads, we attain a failure about 93 kips. When we do for the long threads, we are having failure at 100, roughly 130 kips. That means that to gain full capacity, to take full advantage of our material in the connection, we have to make our threads longer and hopefully attain rupture. takeaway message. So it's longer threads, more capacity. Thank you so much. If you have any question, don't hesitate to reach out.